This is HRW96P086 requested by Jaime, so we're going to use his numbers. Congratulations. Okay, so we've got a sling thrower puts a stone in the sling's pouch. Notice we've got the stone and the pouch's mass. And then begins to make the stone and pouch move in a vertical circle. They give us a radius. The cord between the pouch and the person's hand has a negligible mass, and will break when the tension of the cord is this much or more. Suppose the sling thrower could gradually increase the speed of the stone. Alright, will the breaking point occur at the lowest point of the circle or at the highest point? Alright, it's the lowest point because at the lowest point of the circle, the cord has to have enough tension to, let's see, here's the stone, and say this thing is traveling in a circle. There's the center of the circle. Go on. Okay, not a perfect circle, but whatever. Alright, let's say down here at the bottom. Well, when you're at the bottom, the tension in the string, if I draw a free body diagram of the rock at the bottom, alright, well, it's the rock and the pouch, really. I've got, oh, that wasn't straight at all. I've got the mass times gravity down. I've got the tension up. But I need the total force, the net force, to be equal to the centripetal force needed. So when this is at the bottom of its route, that tension has to be big enough both to have centripetal force, because up toward the center of the circle, and to hold the rock up against gravity. So it's like going to be adding centripetal force and gravity. That's a lot. Okay, whereas when it was at the top, the tension only needs to be enough, or actually the tension doesn't even have to be there. It could be only the centripetal force being provided by the weight of the rock. We could have no tension and it'd be okay. So the bottom's going to be the toughest. What I want to know is at what speed will the stone break the cord. So basically, at what speed does the tension in the cord exceed the amount that it can have before it breaks, which in this problem is 35 newtons. So let's look at that. Let's see. I know that the net force on this rock equals mass times acceleration. This is not zero because I need an acceleration toward the center of the circle because this is moving in a circle. So what I've got is tension pointing up minus gravity pointing down is going to equal, well, I've got the mass times the acceleration for a circle is v squared over r. Okay, basically what I'm saying here is the net force equals, and this whole thing on this side is the centripetal force. That's the net force I need. That's the net force that I have. Okay, so what I get is the tension equals the centripetal force plus the force of gravity. Okay, so at what point will the tension exceed the amount I have? So the amount where it will break is when the tension was 35 newtons. That's from the problem. Okay, I also have the mass. Now we have to be careful here. If you look, the mass is all the mass at the end of the string. So that's the stone and the pouch. Okay, so I've got here is 0.25 plus 0.01. So that's 0.26. Okay, 0.26 kilograms for the pouch. And I've got a radius in this problem of 0.675 meters. Okie dokie. So, go back full screen. Alright, what I've got is that T can't be any more than 35, so I've got 35 equals mass times v squared over r plus mass times gravity. Okay. Now if I do all the numbers that I can do, I get 35 equals, got 0.038, lots of stuff. I'm not going to round yet because I'm not to the end of the problem. We don't round until we're at the end. V squared plus 2.548, which actually, that's as far as it goes, so I don't have to round at all. Okay, cool. Now if I solve for V, okay, move this onto this side, divide by all of this stuff, I end up with 84.25 equals V squared, and then square root both sides. Square root both sides. I'm doing that on my calculator, which you can't see. Huh? And I get 9.18 meters per second equals V. Let's go see what it's supposed to be. 9.18. That's right. Okay. So that's the end of it. Remember, the tension in the string basically was the tension had to be counteracting gravity and providing an additional force toward the center of the circle, which was the centripetal force. So we basically just added those two together and then set it equal to the max tension you could have. So basically even a tiniest little bit faster than this and it would break. Technically speaking, since this is the max tension the cord can take, if you go exactly this speed, you'll be fine. But I mean, we're talking even a millionth of a meter per second faster and it would break.